If you haven't done so yet, please pause the video and try the question on your own before listening on. We're going to begin by determining the rotational inertia of the hoop. And from a table of rotational inertias, we know that a hoop has a rotational inertia equal to 1/2 times the mass times its radius squared. However, that is true only if the hoop is rotating about an axis that passes through the center of the hoop in this fashion. We can see in this case that the hoop is not rotating about this axis. It's actually rotating about this line right here, or this axis. They have the direction of rotation shown by this arrow. The good news is that the ordinary rotation axis is parallel to this rotation axis, so we can use the parallel axis theorem. Now, in this theorem, we know that the rotational inertia will equal the ordinary rotational inertia, that is, the inertia when the object is rotating about its center of mass, plus this term mh squared. H will simply turn out to be the distance from the rotation axis to the axis that passes through the center of mass. So in this case, that distance h will be represented by r, the radius of the hoop. Remember that the rotational inertia about the center of mass was given by this expression right here, so we're going to substitute that in. And again, we've substituted for h the value of r. So these are like terms. They're both mr squareds. We can combine them into a 3/2 times mass r squared. So that will be the rotational inertia for the hoop. Perhaps we can call that I1. Now we'll hold on to this result and we'll refer back to it later. We can next take a look at the square, which of course is made up of 4 thin bars. This thin bar right here will turn out to have no rotational inertia because it is situated directly on the rotation axis, and any object that's directly on the rotation axis will have 0 rotational inertia. As for this bar, what we can do is actually imagine that all of its mass is concentrated in a single point. This would be known as its center of mass. In essence, we can treat it as if it were a point particle, and we have learned that for a point particle, the rotational inertia is simply its mass multiplied by an r squared. Now the r would again be the distance from the point particle to the rotation axis. So the rotational inertia for this bar can be represented as m times r squared. Perhaps we can call that I2. For the remaining 2 bars on the top and the bottom here, we can see that one end of them is aligned right on top of the rotation axis. We learned in an earlier chapter that if a thin bar has a rotational axis through its center of mass, in other words, as if it were spinning around in this fashion, it would have a rotational inertia equal to 1/12 times its mass times its length squared. We can see that the length of the circled bars would be r, because it's a square. So if this side is r, that means this side is r. So we can replace the length of the bar with r. Now this is the rotational inertia of the bar if it's rotating about its center of mass. We can see that the 2 circled bars here are not rotating about their center of mass. They're rotating about an axis that's parallel to the center of mass axis. And therefore we need to use the parallel axis theorem again. So here's the equation for that. And the I center of mass is this term right here, so we're going to plug that in. And then remember that h is the distance from the center of mass axis to the actual rotation axis. And we can see that that distance would be r divided by 2. And then we'll square the r divided by 2. And then these 2 terms can be added together because they are like terms. They both have an mr squared in them. So this would be the final expression for the rotational inertia of this bar right here. That would be the same expression for the other bar right here. So we can say that I3 as well as I4, to represent those 2 bars, are both equal to 1/3 times the mass times the radius squared. Now the total rotational inertia of the system will simply be the sum of the individual rotational inertias. And so when you add up the individual rotational inertias, you should get 19/6 times the mass times the radius squared. And now we can recall that the radius was given to us, as was the mass, so we can plug those in. And when we compute that, we should get approximately 1.6. And the unit will be the unit of mass, which is kilograms, times the unit of distance, which is meters, of course. That unit of distance needs to be squared, so you'll end up with kilograms times meters squared. And that will indeed be the correct answer to part A. For part B, we're going to first calculate the angular speed, which we know is the angular displacement divided by a time interval. The question notes that the period of rotation is 2.5 seconds. What that means is that it takes 2.5 seconds for this object to spin around one time. And when an object spins around once, it has traveled an angular distance of 2 pi radians. So the angular distance will be 2 pi, and it did that in 2.5 seconds. And so the angular speed turns out to be roughly 2.51 radians per second, and we're going to use that to calculate the angular momentum. Since the angular momentum, which is symbolized by L, is equal to the total rotational inertia multiplied by the angular speed. And so we plug in those values, and when we compute that, we should get approximately 4.0, and then the unit is kilogram times meter squared per second. The radian can be excluded from the unit at this point, so we have the kilogram times meter squared all over seconds. And that is indeed the correct answer to part B. Thanks for taking the time to watch the video. If you liked it, please subscribe to the channel so you can stay tuned for additional videos. Also, you are welcome to send in your own question to this email address, and I will do my best to provide a video solution